So hello and welcome everyone. So in this video, we are going to solve the question transitive closure of a graph. So first of all, let's try to understand what the problem is trying to say. So let's start. So in this question, you will be given a directed graph and you have to determine whether a vertex j is reachable from another vertex I for all vertex pairs I, j in the given graph. So that is what it means by transitive closure. Here vertex j is reachable from another vertex I means that there is a path from vertex I to vertex j. The reachability matrix is called the transitive closure of a graph, and the directed graph is represented by an adjacency matrix where there are n number of vertices. So don't worry if you are not able to understand the problem statement. So I'll be explaining you what it means by transitive closure. So first of all, let's take the example number 1 mentioned over here and let's try to understand. So I've taken the example number 1 and over here, this is the adjacency matrix for this example number 1. So now what I'll be doing, let me construct the directed graph for this one. So if I construct the directed graph, I can see there is a directed edge from 0 to 1, and from 0 I can see there is an edge to 3, right? And from 1 I can see there is a directed edge to 2, and from 2 I can see there is a directed edge to the node 3. So this is the directed graph for this example number 1. Now what is the transitive closure? So transitive closure is nothing but a matrix. Okay, it is n cross n matrix. There will be 0, 1, 2, 3, n number of nodes, and there will be n number of rows and n number of columns. Okay, 0, 1, 2 and 3. So this is the matrix there, or you can call it as transitive closure. So what are the values stored inside the transitive closure? So let's say in this 0th column that represents the node 0, I have to write down how many vertices are visited, how many vertices can be visited from node number 0. So let's start. This is my node number 0. From 0, how many vertices can I visit? From 0 I can reach the vertex 0 itself. I can go to 1. I can go to 2 and I can reach the vertex 3. So I can visit 0, 1, 2 and 3. So inside this transitive closure or this matrix, what I'll be doing, I'll be marking how many nodes are visited, how many nodes can be visited. So I can see 1 can be visited, 0 can be visited, 2 and 3 can be visited, right? So similarly, we will be finding for the other vertices as well. So let's try to find for 1. From 1, how many vertices are visited? I can visit 1, I can visit 2 and I can visit 3. So I'll be writing down 1, 2 and 3. Similarly for 2, how many nodes can be visited? I can visit 2 itself. I can visit 3 also, right? And for 3, how many nodes can be visited? I can see only the node 3 itself because it does not have any directed edge, right? So these are the vertices which can be visited. So inside the transitive closure, I can write down for 1, I'll mark 1, 2 and 3 as visited. So I'll be marking down the other vertices as 0. That means it cannot be visited. For 2, I can see 2 and 3 only can be visited, none other nodes, right? So I'll be writing down 0. For 3, I can see only 3 can be visited, and for the other nodes, I'll be writing down 0. So this is the transitive closure, and hence you can observe in the output, we have got the same output as this one. And this is the transitive closure for the given graph. I hope you understood what it means by transitive closure, and that was all about the question. So now let's try to understand how to solve this question. So in order to solve this question, I'll be showing you 2 different approaches, and I'll be giving you the idea how to solve it with the approach number 1 and what will be the time complexity and space complexity, as well as with the approach number 2. So let's start with the approach number 1. So the approach number 1 is using the DFS algorithm, and okay, so in this approach number 1, we are going to use the basic DFS algorithm. So let me just copy this entire directed graph and let's try to find the transitive closure. How will we find the transitive closure? So this is the directed graph for which we are going to find the transitive closure. So in this DFS algorithm, what I'll be doing, I will be applying the DFS algorithm from each and every node present inside this directed graph. And for each and every node, what I'll be doing, I'll be keeping a list of all the nodes that can be visited. And I'll be marking all those nodes inside the transitive closure as 1. So let's say if I'm applying the DFS for this graph now for this node number 0. So as I mentioned, I'll be applying DFS for every node. So that will be from I to 0, I is equal to 0 till I is lesser than n. And I'll be applying the DFS algorithm. Okay. So now if I apply the DFS from 0, so DFS of 0 will be giving me how many nodes I can visit. I can visit 0 itself. From 0 I'll be going to 1, and from 1 I'll be going to 2, and I'll be going to 3. So I'll be keeping a list of all the nodes that can be visited. So I'll be getting a list as 0, 1, 2 and 3. Similarly for DFS of 1, I'll be getting a list that says if I start from 1, I can visit 1, 2 and 3, right? So I'll be having 1, 2 and 3 inside this. And for DFS of 2, I can see node number 2 and 3 can be visited, right? So 2 and 3. And for DFS of 3, I can have only one node that can be visited. See, this is the DFS algorithm which I'm applying on each and every node. So in general DFS algorithm, if I'm using the DFS on a directed graph, general traversal technique, so at that time you might be using a visited array, right? So you'll be not calling the visited, you'll be having a visited array, and if the node is visited, you are not going to make a DFS call, right, in this for loop. But over here you are not going to use any kind of visited array when you are not applying the DFS algorithm. Inside the DFS algorithm, obviously you require a visited array, but outside the DFS, whenever you make a DFS call over there, you are not required to use the visited array. Okay, I'll show you the implementation part, but this is how the DFS algorithm can be useful. So now if I observe what is the time and space complexity of this approach, then let's try to find out the time and space complexity. So before understanding the time and space complexity, we need to have a clear understanding that what kind of graphs are possible in the question. So in the question, it has been mentioned that only directed graph. It is not mentioned that the graph will not contain any cycle. Okay, so that means what will be the time and space complexity? Okay, so over here, this code snippet already shows that we'll be having a for loop, and this for loop will be iterating n number of times. Fine. Now over here in the directed graph, what is the time taken for the DFS function? So in general, we know the time complexity of the DFS function. It is going to take order of v plus e, right? Absolutely correct. Now over here, how many vertices are possible? So the total number of vertices can be v. Now how many edges are possible? So that is the question. So the answer will be different if I talk about the worst case kind of graph. If I take an example of a dense graph, so how many nodes are possible? Inside a dense graph, for every pair of vertices, you will be having a direct edge. So let's say if I have 3 vertices, 0, 1, 2, and now if I want to show you an example of dense graph, so there will be an edge to every vertex from 0 to 1, from 0 to 2. For 1 also, it will be having an edge to 0 as well as to 2 as well. For 2, it will be having an edge to all the other nodes. It will have an edge to 0, it will have an edge to 1, right? So how many vertices are possible? Okay, so let's, how many vertices, I mean how many edges are possible? So let's try to find out the number of edges. So for each and every node, how many edges are possible? For each and every node, v minus 1 number of edges are possible, right? It will have v minus 1 number of neighbors, every node. So how many nodes are there? I can see v number of nodes are there. So for a dense graph, the total number of edges will be v into v minus 1. So over here, I can replace this e by v into v minus 1. Absolutely fine. So the DFS, the time complexity of DFS comes out to be order of v plus v into v minus 1. This is the time complexity of our DFS algorithm. Okay, fine. Now I am applying the DFS on each and every node. So this time complexity can be implemented it is mentioned over here, right? I can mention it over here. So that means the outer for loop is going to run n number of times, or you can say v number of times, that many nodes are possible. So the overall time complexity of this approach will be order of v into v plus v into v minus 1. V into v minus 1. Or I can write it as v into v plus v square, right? Or I can say it v cube plus v square is the time complexity of this approach. Okay, and overall I can just write down it as order of v cube. And what about the space complexity? Space complexity depends upon how many extra variables or how many extra arrays you are going to create. So let's take the space complexity as order of v square, depending upon the visited array which you will be using to store the answer. So the space and time complexity are as mentioned. So this is going to be your space and time complexity of this approach. Order of v cube plus v square. But overall it is not order of v cube, it is order of v cube plus v square. The answer of this. Okay, fine. So now let's have a look at the implementation part. So this is the implementation which I have done, and this implementation is written in Java, but the same can be implemented in other languages as well. So let's try to understand. So first of all, over here I have created a Boolean matrix. You will be capable of understanding why I have created a Boolean matrix. Basically, this Boolean matrix will be storing the answer. See, this function is transitive closure function, and it returns an array list of array lists, right? Now I'll be applying the DFS on each and every node. See, I have not used any visited array. So I'm applying the DFS from beginning for each and every node. So let's have a look at the DFS function. So inside the DFS, there are this many arguments. The first is the root. That means from which node you have started this DFS call. This second argument is the current node. That means in your DFS, which is the current node. The third argument is the graph. The fourth is the visited array. Inside the DFS, currently you will be marking your visited array, right? And this is the Boolean matrix or the transitive closure. So now first of all, on visiting, I'll be marking the current node as true, and then inside the transitive closure matrix, for the root node, I'll be marking that current node is visited. I can visit the current node from the root node. Now I have applied the DFS on all the adjacent nodes. I'll be checking if that node is not visited in the DFS tree, and if there is a direct edge to that node, then I'll make a DFS call. So I have passed the root node, the current node will be I, the graph, and the visited array and the Boolean matrix. So this is the DFS call. This is the entire DFS function, and now after applying the DFS, the entire matrix MAT will be containing your transitive closure. Fine. But the answer needs to be returned in an array list. So I have created an array list, and what I'll be doing, I'll be simply filling out this array list of array list. So the outer for loop, n number of times, I have inserted a new array list of size n, and then I have iterated over all the elements starting from 0 till n. And now what I'll be doing, I'll be checking if mat of I comma j is equal to true. That means that node j can be visited from I. If it is true, then at the relevant position, that is at ith index and jth index, that is at I comma j in answer array list, I'll be adding 1, else I'll be adding 0. And I'll be simply returning the answer array list. So this is the entire implementation, and if we want to check this acceptancy, let's try to submit this solution. And we can see that the problem was successfully submitted. So this is the approach of transitive closure of a graph using DFS. Now I'll be showing you the other approach as well. But the time and space complexity, what is the time complexity of this approach? The time complexity is order of v cube plus order of v square. And what about the space? See, the space is equivalent to order of n square. Basically, total number of vertices is n, that's why n square, or you can say v square. So now let's try to see the different approach in which the time complexity will be strictly order of v cube. So now let's try to understand how we can solve this question using the second approach, and that approach is going to use Floyd-Warshall's algorithm. So basically, if you have forgotten what is Floyd-Warshall's algorithm, just let me give you an idea about how this algorithm works. So this algorithm is used to find all pairs shortest path. So this algorithm is nothing but all pairs shortest path algorithm. So basically how this algorithm works. So let me give you an idea of, using the same example over here, which we have taken over here. So let's see. So let's say this is the directed graph for which you have to find out all pairs shortest path. So what is all pairs shortest path? So basically, let's say this is a directed edge weighted graph and all the edges are weighted as unit weights. So now this Floyd-Warshall algorithm will help you to find out that what is the shortest path to reach the vertex 1, what is the shortest path to reach the vertex 2, and what is the shortest path to reach the vertex 3. If there were other more vertices like vertex 4, 5, 6 and so on, then this algorithm will help you to find out for particular vertex what is the shortest path to reach any other vertex present inside the graph. So this algorithm, let's say we have a matrix called as distance matrix. So this algorithm will help you to find out the shortest path for every pair of the vertex in the graph. So 0, 1, 2 and 3, 0, 1, 2 and 3. So now I can see what is the shortest path to reach 0. 0, 0 can be reached with a distance 0. From 0 to 1, what is the shortest path? 1. From 0 to 2, the shortest path is via 1. That is 1 plus 1, that will be 2. Now I can reach the vertex 3 from this path and I can reach the vertex 3 from this path. Which is the shortest one? This is 3 and this is 1. So it will be shorter one will be 1. So in this manner, for each and every vertex, you will be able to find out what is the shortest path to reach any other vertex. I hope you understood what the Floyd-Warshall algorithm does. So now let me help you how this algorithm works. What is the fundamental concept on which this algorithm is going to work? So if you want to know more about this Floyd-Warshall algorithm, then after this lecture, have a look at how this algorithm works and have a look at what is the proof of this algorithm. Okay, so now let's start. So let's imagine there is a graph that says 0 to 1 directed edge and the edge weight is equivalent to 12, and now let's say 0 to 2 and 2 to 1. So now let's say this edge weight is equivalent to 3 and this edge weight is equivalent to 2. Now let's say if I want to find the shortest path from 0 to 1, shortest path from 0 to 1. So how will I do that? This is 0 and this is 1. I can see one path is weighting 12, this path, and the other path, if I go via 2, it is weighting only 3 plus 2, that is equivalent to 5. So the shortest path from 0 to 1 has weight equivalent to 5. So this process is called relaxing of a node. So this is what it means by relaxing. So the entire Floyd-Warshall algorithm is based upon this relaxing concept and how this concept is working. So let's say if you have any other vertices, any pair of vertices u comma v. Now let's say if you want to find the shortest distance between u comma v, you will be including any other foreign node, that is k, and you will be checking if I go via k and reach the vertex v, whether I'll get a shortest path from u to v or not. So I'll be including the path u to k and I'll be including the path from k to v, the shortest distance from u to v, in order to find it. So basically, this is how the Floyd-Warshall algorithm is going to work. So that was a short introduction about Floyd-Warshall algorithm, and now let's try to see the implementation part of this algorithm. But before moving on to the implementation path, let me show you the important comparison which is required. So let's say over here inside this example, this is the node u, this is the node v, that is starting node and the ending node, and the intermediate node is called the node k. Now let's say if the distance of, I want to find the distance of u to v. If this distance, whatever distance we have earlier, if that distance is greater than distance from u to k, the path from u to k plus distance of k to v, if this inequality is satisfied, then obviously I'm going to update the value of distance from u to v. That is basically the shortest distance, right? So let's see the implementation part of Floyd-Warshall algorithm quickly. So this is the implementation part. The implementation of Floyd-Warshall algorithm is pretty much shorter as compared to the actual explanation of the Floyd-Warshall algorithm and the proof of this algorithm. So over here, you can observe the outer for loop is working on the intermediate node. It is iterating over all the intermediate node. I am going to include one by one each and every node present inside the graph as the intermediate node. And now the inner for loop is working on the source node, that is from which node I am going to find, and I have called it as I. The inner for loop is going to work on the destination node. I am going to find the shortest distance from source to destination, that is from I to j, by including node k as the intermediate node. So now if I see if the distance from I to j, the previous distance is greater than distance of I to k plus distance of k to j, then obviously I need to update the value of distance I to j. So this is the Floyd-Warshall algorithm. This code snippet I'm going to use inside my algorithm. So that's why I've shown you how this Floyd-Warshall algorithm is going to use. So now let's try to understand how we are going to use this algorithm in order to find the solution of our question. So let's try to solve the example and get the transitive closure of the graph done. So now let's take an example. Let's say this is the same example one which is given to us, and imagine this is an directed edge weighted graph with unit weights. Fine. Now what I have done, this is the adjacency matrix which will be given to us in the input. Now I will be requiring a distance matrix, and the Floyd-Warshall algorithm will be working on this distance matrix. So basically this entire algorithm, this code snippet is going to work on the distance matrix. So now let's try to find the first step of our algorithm is to fill the distance matrix. So if I ask you a question, let's say if you want to find the distance from u to u, basically let's say if I want to find the distance from the current node to that current node, what is the minimum distance? So you will be saying 0. Absolutely correct, right? So over here for every I comma I, that is 1 comma 1, 2 comma 2 and 3 comma 3, I'll be putting down the value as 0. Whenever I see the comparison that the source and destination are equal, the distance will be 0. Now let's try to find out what is the distance from 0 to 1. The graph is unit weighted. So from 0 to 1, I can see the edge weight is present, the edge is present. So wherever the edge is present, I'll put the distance matrix value as 1. So 0 to 1, edge is present, so I'll be putting at 1. So from 0 to 2, is there any edge present? No, there is no edge present. So at that position, I'll be putting infinite. That is the shortest distance from 0 to 2 is infinite. Now from 0 to 3, edge is present, so shortest distance, basically the distance will be 1. Now for this one, 0 is present inside the adjacency matrix, so it will be infinite. 1 is present over here, so it will be 1, else infinite. Wherever 0 is present inside the adjacency matrix, I'll be putting down infinite. And for 1, I'll be putting down 1. Over here, infinite, infinite, and infinite. So this is the distance matrix. And you can imagine this as a directed edge weighted graph. This is the entire directed edge weighted graph. And now what I'll be doing, I'll be applying the Floyd-Warshall algorithm. So this is the matrix that you will be getting after applying the Floyd-Warshall algorithm. So you can apply this Floyd-Warshall algorithm as it is going to take n into n number of steps, and for this example it is going to take 4 into 4 into 4, that is 64 steps. So it will be very much lengthier to explain. So what you can do, you can try out the dry run on this distance matrix and check whether you are getting this distance matrix or not after applying the Floyd-Warshall algorithm. After applying the Floyd's algorithm. Okay, so this is the distance matrix that I will be getting. So now this was the first step, that is initialization of the distance matrix. The second step was to apply the Floyd-Warshall algorithm, right? And the third step is to find out the transitive closure. So now it is very much easy to find the transitive closure. Why? Because let's say, as we have already found that what is the shortest distance and what is transitive closure, we have to check for any pair of vertex whether you can reach from u to v or not. So this Floyd-Warshall algorithm can help you to find out whether how many nodes, basically how many nodes can you visit from the node number 0. If the distance present inside the distance matrix is not equal to infinite, then that means there is a path possible. So over here, what you can do, instead of distance, you can just replace all the not infinite values by 1. So I'll be replacing the entire first row with the value 1. I'll be replace this by 1. I'll also replace this by 1. This is already 1, and I'll replace this 0 by 1. Every value which is not infinite, I'll replace them by 1. So this becomes your transitive closure. Isn't it very much simpler to do with the help of Floyd-Warshall algorithm? Yes, it is. So this is the transitive closure which we are supposed to find. This is the transitive closure of the graph. I hope you understood how to find the transitive closure with the help of Floyd-Warshall's algorithm. And now I'll be mentioning out each and every steps of the algorithm so that you can implement in your own languages, right? So what are the steps of algorithm? So the first step is to find the distance matrix, right? What is the second step? Second step is to apply the Floyd's algorithm. And what is the third step? Is to find the transitive closure, right? So this is the algorithm to find the transitive closure of the graph. I hope you understood each and every step. And now what we'll be doing, we'll be seeing the implementation part, how we can implement this each and every steps. And I'm going to use the same Floyd-Warshall algorithm which I have mentioned over here. So let's start the implementation part. So this is the entire implementation of Floyd-Warshall's algorithm. So over here, I have implemented the entire algorithm in so-called Java programming language, but the same can be implemented in other languages. Okay, so I have written down each and every steps. So the first step to find the transitive closure is create the distance matrix. So I have used a distance matrix of size n cross n, and the data type has been kept as long. Because I'm going to use infinite over here, so I have used the data type as long. So now this is the for loop. I'll be iterating over each and every vertex starting from I is equal to 0 till I is lesser than n. The inner loop from j is equal to 0 till j is less than n. Now if I see if the graph of I comma j, that is the adjacency matrix, says that edge is present, so inside the distance matrix for I comma j, I will be adding 1. That is the distance from a particular node to the adjacent node will be equivalent to 1. Else what I'll be doing, I'll be using the distance as infinite, because if the edge is not present, then I'm going to find the shortest path. If the direct edge is not present, then put it infinite. And one more thing, as I mentioned, that the distance from current node to current node is equivalent to 0. So if I and j are, if the source and destination are equal, then distance will be equivalent to 0. So that was the first step to prepare the distance matrix. And now let's try to find how to find the Floyd-Warshall algorithm, basically applying the Floyd's algorithm. So the outer for loop runs on the intermediate node. The inner for loop runs on the source node. The inner for loop, that is j, runs on the destination node. So I'll be checking whether the distance from source to destination, that is from I to j, is greater than the distance from I to intermediate node, that is I to k, plus distance of intermediate to j, that is distance from intermediate to destination. If this is true, then update the value of source to destination distance with distance of I to k plus distance of k to j. So this is the entire Floyd-Warshall algorithm. And now what I'll be doing, I'll be using the answer list. So the third step was to find the transitive closure, right? And this algorithm, this function returns an array list of array list, as we already saw, right? So I need to convert it into array list of array list in order to return the value. So I have created an array list of array list that goes by the name answer. Now I'll be using a for loop on each and every position of the array list, and I'll be inserting an empty array list of size n, and then again I'll be iterating over each and every vertex, that is j is equal to 0 till j is lesser than n. Now if I find inside the distance matrix, if the value is infinite, then that means that node is not at all possible to visit. So inside the list of list or array list of array list for I, I'll be putting the value 0. That is from I to j, no path is possible. So I'll be putting the value 0. Else if the value is not infinite, then that means the path is possible, and I'll be putting the value 1. So this is how I prepare the answer list or find the transitive closure, and at the end simply return the value of the answer, right? So now let's try to see the acceptance and let's try to submit the solution. And we can see that the problem has been successfully submitted. So now what will be the time and space complexity of this approach? Let's try to analyze. So first of all, let's see what will be the time complexity. This is n square, right? The outer for loop and the inner for loop n times, so n square. Now the Floyd-Warshall algorithm, it takes order of n cube time. So I'll mention the time complexity over here as well. This will be taking order of n cube. this loop is going to take order of this step, that is basically distance matrix, order of n square, and this last prepare the answer list, it is also going to take order of n square. So the overall time complexity of this approach comes out to be order of n cube, because that is the significant term. It is not order of n cube plus n square just like the previous approach, right? So this is the time complexity, order of n cube. And what about the space complexity? I have used only a distance matrix apart from storing the answer inside the array list of array list. So the space complexity of this approach comes out to be order of n square, right? So this was all about the transitive closure of the graph. I hope you understood how to solve this question. So if you enjoyed the video, if you enjoyed the solution, do hit the like button and share it with your friends, and do comment down how did you find this video. So that was it for in this video. I hope you understood everything. Thank you for watching, and we'll see you in the next video.